New in LooseS version 24, we have improved design combination generator and design calculations for post-tension structures in accordance with Eurocode 2. To demonstrate these new features, we're going to carry out analysis and design checks on a 3-span continuous post-tension voided slab bridge. Here we can see the overall dimensions and cross-section here showing the voids. The blue lines represent the tendon profiles. In general, these follow the bending moment diagram under dead load and allow these types of bridges to have longer spans. Now, if we go to our LooseS model, here you can see you've idealized the bridge as a grillage. If we look longitudinally, turn on the fleshing, hide our diaphragms, we can see that the longitudinal members are centered on the webs. This is convenient for the tendon assignments too. We can check the sections here. If we look at the longitudinal sections, this was created with the arbitrary section property calculator. Similarly, for the transverse, we've used a compound section representing the thinnest part over the voids. And we've also got a torsion reduction applied to the members due to the grillage assumptions. It's a 3D analysis category, and we've got the piers and abutments idealized as point supports where the bearings are located. If we go to the analysis tree view, we can see we've already set up our base analysis with gravity, thermal load, surfacing. We've got a pre-stress analysis, and we've got some traffic load using the vehicle load optimizer. Now to show the first development, the design combinations have been completely overhauled. So if we go to design combinations, here you can choose the country. We're going to do Europe as we're doing Eurocode 2 design checks. There's an option here to create load cases for selected code. This will create a series of placeholder load cases with naming to speed up your generation of models. If we press OK, we've now set that, and we can go to design combinations, generate design combinations. And this will automatically find names of load cases that will associate with a certain action. But if the automatic association is not correct, you can still go in and add load cases here, choose any load case, and associate it with an action. And you can see here it's already showing a table of what the different loading factors will be. So here we've got our permanent actions, we've got pre-stress, gravity, and surfacing. And variable actions, we've got our thermal load and some traffic loading. Then we go to combinations to generate. Here we can select which combination types we want. These I've selected for the design checks we're going to be doing later. We can also choose the type of combination to generate, basic, smart, or separate load cases. And we can also click on review combinations here. And this will give us some overall tables for each of our combinations so that we can see an overall picture. This makes it quick to review and make any adjustments that you may require. Here as well, we've got the option to create envelope for each combination, which I'm going to use. And this option here, delete existing combinations, means that you can quickly recreate a different set of combinations and it will replace them rather than having duplicates. So I'm going to generate combinations. And just like that, it's created each basic combination, and then an envelope for each combination type. We've got characteristic, SLS, SLS frequent, and ULS fundamental. Now if we look at our pre-stress loading in a bit more detail, I'm going to set active this first load case here so we can see the tendons, and I'm going to turn on transparency. So we've got 3 load cases in this pre-stress analysis. You can see that there's no nonlinear controls on, but because we've got the pre-stress assigned, we've got this option here. And by default, this is on, and we'll see later on how these primary effects are used by the design tool. The tendon profile and properties are defined in the utilities tree view, so we can just have a look at the property here. We've chosen losses based on time inputs and calculated stresses, and design code of Eurocode 2. Here's where we can set our tendon area and tensile strength. We've also got our tendon profiles. With just a few data points, we can define that parabolic profile. If we look side on view, you can see that a bit more clearly. I should note that by local coordinates mapped to lines option here means we only have to define this once, and then we can assign to each set of longitudinal lines. If we go to the attributes tree view, we can see this is where those utilities are pulled into and where you can set your pre-stress force. If we go back to the analysis tree view and have a look at how this pre-stress analysis was set up, expand the loading folders, what you can see is we've got an initial case, which is gravity and the pre-stress load. The next stage we've got surfacing as well as the gravity and tendon load. And then the third load case is the same loading but for an extended period of time to get our long-term effects. The duration of each stage was determined from the bridge time management. And here we can go to our pre-stress analysis, and here you can see the duration of each stage. Because we've chosen linear elastic, this means that our pre-stress losses are accurate and also allow for combination with other loads for our design. Having it set up like this allows us to get a range of different pre-stress loads from initial right through to long term. If deflections were of importance, then you would need to use a material nonlinear in the time domain, but we're not doing that right now. Our permanent loads are applied in this pre-stress so that the pre-stress losses are based on accurate stresses. But for design purposes, we need to isolate those pre-stress forces. So we've got some 3 simple basic combinations, and it's simply our total effects from each pre-stress case minus the other permanent loading we had at that stage. So here we've got gravity and superimposed dead load taken off from the pre-stress at that case. And finally, long term minus self-weight and superimposed dead load. And then we've just created an envelope of those 3 isolated pre-stress combinations. This makes it easier for our design checks to make sure we're not missing anything, whether instantaneous case or the long-term case is more critical for certain checks. Now we can get on to the design. So if we go to design, concrete frame design, I'm going to choose Europe and Eurocode 2. I'm going to leave these defaults as they are, okay. And then we need to create a design attribute. So if we go to attributes, design, concrete frame design. So notice that these steps are the same whether it's reinforced concrete or reinforced and post-tension. But crucially, this is the frame designer, so it works on beam elements rather than any shells. Here we can check the specific parameters used for the design checks. You can go through each tab, check the defaults and see if you want to make any adjustments. For our service limit state tab and our allowable crack check, we're going to change this option to the standard 0.2mm crack check. There's also the option for more strict cases to ensure that the concrete immediately surrounding the tendons remains entirely in compression. That would be this decompression check. So I'm going to press OK on that. I've actually already got one assigned, but this you would just assign to any of the lines that you wish to do the concrete frame design on. So for this example, I've just assigned it to the central longitudinal girder. Now the software will automatically account for where the tendon profiles are in the design checks, but for any passive reinforcement, these need to be defined. If we go to the utilities tree view, we can see here that I've got a section longitudinal rebar here. If I double click on that, so we've got the shape outline from our longitudinal section, and here I've chosen to have 5 25mm diameter bars at, this equates to 200mm spacing on the bottom and top faces, and we've got 50mm of cover. For this example, we've just got simplified reinforcement that's constant throughout, but you can define as many layers and changes as you would like for your specific cases. Once that's defined, we also have the line reinforcement. This is where you tell the software for how long over the line each reinforcement section is acting. And these utilities are accessed from the utilities menu up here, and then reinforcement. Once they're defined as a utility, all we have to do is, in our section attributes, we can just choose that in here, and we can see we've already chosen our longitudinal rebar line. In addition, we need to make sure we've got a reinforced concrete material attribute. So here we've got C40 concrete, and we've got 500B steel reinforcing bar. And we need to make sure that this is according to the code we're checking. If we specifically look at the concrete in this case, we need to use this advanced define option, as we're using the pre-stress losses based on time. Now we can set up our load set for design. So if you go to design, concrete frame results, and we can choose here which checks we want to carry out, and also identify the correct load combinations to use. So for this example, I'm just going to be carrying out these 3 checks here: ULS bending and axial, SLS stress limitation, and SLS crack control. And we can go in here, and for ULS, I'm just going to use my ULS envelope. For SLS characteristic, I'm going to choose this envelope here. And SLS for cracking, I'm going to use our SLS frequent case. And you can also choose the extent to which you want the design to be carried out on. For this example, I'm just going to use a group that I've created of a few locations of interest. Okay. And you can see this comes up in our analysis tree view here. And those lines I chose to carry out the design are just a group that I've selected here. So you can see we've got mid-span at the pier and then mid-span of the shorter span. So if we go to the analysis tree view, we can right click on this concrete frame load set. I'm going to go show results. So now the calculations have taken place. We can see we get our results table here. Firstly, we have a summary. We can see that for ULS and for stress limitation SLS, we're just about okay, but we're failing our crack width check. So if we go over to that SLS crack control, just expand this a bit, and we can filter this to get the worst at the top. And if I double click on there, we can get some detailed results. We can see here that on the right hand side, our cross section where the tendon is shown in cyan, and we've got our reinforcement bars shown there as well. We can see all the inputs and calculations, and if we go right down to the bottom for the final check, we can see the crack width calculated is 0.27 millimeters, which is above our allowable. Now there's a few ways in which we could make some design changes to get this to pass. One could be changing the reinforcement, the passive reinforcement. But for the purpose of this example, we're going to see if we can adjust the pre-stress loading to get this to pass. So I'm just going to close these. And if we go to our tendon property definition here, open that up. And I'm going to increase the area of this tendon to 3,300 millimeters, which is equivalent to 22 of the same strands. Okay. That's come up in the as another input there on the utilities tree view. And then I'm just going to go into my tendon load, change that property. Now, because we've increased the area of the tendon, we can also increase the force. So I'm going to increase that to 4.4 E3. Okay. And we now need to resolve that pre-stress. Now that's solved and results are loaded, I'm going to ask for the design results again. So I'm going to right click on here and show results. Now the design calculations have been carried out. We can see that we've got everything below a utilization of 1, so passing. You will notice that the utilization of stress limitation has increased a bit now. So often it's a balancing act between these two SLS checks here. If we go to the ULS bending and axle check, we can see that you can, if we just deselect those lines, if you're not sure where one of these checks is coming from, then you can use this select lines and model option, and then that will select the line where the check is coming from. I'm just going to order this in terms of highest utilization. And out of interest, I'm going to check the location where there's hogging. So you can see here we've got this positive bending. And again, I can use the select lines and model to see where that's coming from. That's right there over the pier. And if I double click on that to get some detailed results, And on the right hand side, we can see we've got the section at ultimate resistance, and we've got the cracked concrete here. We've got the location of the tendon, obviously nearer the top fibre, and our reinforcement. You can also check the section at loading. And if we scroll down, we can see the loading, and you can see here primary effects of pre-stressing not included. And so this is where the design check tool has automatically recognized from our pre-stress analysis what our primary component is. That's the primary pre-stress component, so the P times E. And for ULS checks, we need to make sure these are taken off the applied load because we're using the pre-stress on the resistance side. And again, you can scroll down and see the final utilization of 0.66 for this section over the pier. This is just one way to view results from the concrete frame check. You can also view contours if that's more convenient.